Okay, gang, today we're going to talk about the extraordinarily exciting topic of conjugate addition. I hope you're extraordinarily excited because it is extraordinarily cool. All right, so here we have our good old friend methyl lithium, and it's going to attack this nice conjugated carbonyl. Why do we call it a conjugated carbonyl? Because there's a double bond next to the carbonyl. And of course, what it's going to do is the methyl is going to attack the carbonyl. But I'm of course asking you for a second product because the major product is here, but what's the minor product? And you've all done your homework, so you know the answer to this. What are we going to do? We're going to get a conjugate addition. What does the conjugate addition means? It means the methyl group is going to attack out here on the double bond, pushing the double bond into this position, making an enolate temporarily. Then the water workup will give us our final product. So which product do we get? Well, the methyl is going to add over here. It's not going to add to the oxygen, so that's guy out. It's not going to add to that alpha position. That's ridiculous. It's going to add to the beta position, but also E is just plain weird. So, but is it C or D? Well, the key thing is, remember, you're adding a methyl and a proton, so the double bond is going to be gone. So the product we get, of course, is D, and that's the conjugate addition product. Now, it's a minor product. Why? Because the methyl is a very reactive nucleophile. It sees that carbonyl carbon. It knows that's the center of positive charge. It goes directly for the most reactive center. And the lithium, of course, is associated with the oxygen. So you're adding that lithium methyl across the carbonyl. Now, this minor product, though, is called conjugate addition, and it's a really important reaction. It just happens to be minor in this case. And the interesting thing about it, if you compare the stability of these two things, the minor product is definitely the more stable one because it's got the carbonyl, which is a very stable group. This has got steric hindrance here, so the minor product is sterically better and is thermodynamically the better product. So this is a case of kinetic control. The major product is definitely a kinetic product. Now, for reactive nucleophiles like the methyl lithium, we get that kinetic product. But if you have a less reactive nucleophile, then you can get the thermodynamic product with the conjugate addition. So if you think about relative reactivity, that's going to be the key to all this. So here's the mechanism for. I'm sorry, I'm ahead of myself. Here's the mechanism for the conjugate addition. Follow the green arrows. You tack over here on the beta carbon, and you form this enolate, which gets protonated to give the minor product. Okay, so here's an example now of what I was mentioning before, of a less reactive nucleophile. Cyanide's a very good nucleophile, but it's not nearly as reactive as a methyl minus. So HCN, you'll protonate the carbonyl, yes, but more importantly, the cyanide is going to attack out here at the beta position, go to this enolate, which picks up the proton from the HCN. And this is conjugate addition with a cyanide. And it's a weaker nucleophile than the methyl lithium. Here's another example, a simple amine. Amines are good nucleophiles, but again, they're not that reactive. You think of it as an amine as a base, but it's not nearly as strong as base as the methyl of methyl lithium. So this is a much poorer nucleophile than a lithium reagent. And again, it'll do a very nice conjugate addition. You'll first get this ammonium ion, and then you'll do an internal transfer to tautomerize that proton to give you the final product, which is an amine. So this is actually a good way of making amines if you happen to have an amine where it's a beta to a carbonyl. Okay, so this will go back to the methyl lithium one where we have the major and minor product. And so the question is how could you improve the 1,4 yield? What if you really wanted the minor product instead of the major one? How could we make the methyl lithium basically add do conjugate addition so we could get the thermodynamically more stable product? Well, the problem is, of course, is that the methyl lithium is so reactive. And what we need to do is we need to figure out a trick to make the methyl lithium less reactive. So we're looking for a less reactive form of methyl minus. Well, it turns out we already have one. And because what we're looking for is what we call a softer methyl minus, where we've toned down its reactivity. And the secret was these organocopper chemistry, which we talked about back when we were doing organometallic. Remember Henry Gilman, the father of organometallic chemistry? He was this absolutely amazing chemist who was actually blind and did just published hundreds and hundreds of papers in organometallic chemistry. But anyway, his Gilman reagents, which is copper with 2 R groups on it, are the secret, because they are less reactive by far than the lithium reagents themselves. Now these are easy compounds to make. Here we have ethyl lithium, 2 moles reactive with cuprous iodide, and you form this diethyl cuprate, a Gilman reagent. Now these can only be made by simple primary alkyl lithium, so it's not a general solution. You can't use some complicated compound to make these, because they wouldn't be stable. But simple, linear primary ones, you can make them just fine. And it turns out if you react your conjugated carbonyl with a Gilman reagent, it'll very cleanly do 1,4 addition, and the minor product is now the major product. In fact, these are very good yields. Now this seems like a good solution, but it's got some inconveniences here, because you have to make the Gilman reagent, and one of the problems, of course, in the Gilman reagent, you have to throw half of it away, because you're adding only 1 methyl here, the other one doesn't add. So, but it turns out there's a solution to this one too, which makes this really useful, and that is that you don't actually have to use the Gilman reagent. You can just throw in catalytic copper. So if you just take your methyl lithium and you throw into it 1% cuprous iodide, what'll happen is that the methyl lithium will react to the copper first, and then the copper, the methyl copper, you're essentially making the Gilman reagent as you go along, and then that methyl from the copper will do the 1,4 addition. So this is a really good solution. You just throw in the cuprous iodide and you switch over to conjugate addition, 1,4 addition. So let's do one of these. Here we have a conjugated carbonyl, and we're going to use butyl lithium, and just for fun, we're going to throw in our cuprous iodide. And so what's the product going to be? Well, we're going to do conjugate addition, right? And so we're going to add to the 1,4 position. So what's the answer? Well, you all know, because you have nothing else to do this morning except pay attention to the video, so you understand this absolutely perfectly. And what does it give? Well, of course, it gives A. Yeah, so we're going to get A, and that's a clean example of conjugate addition. How would you make B and C? Just while we're at it, that's not really part of the question, but how would you do that? Well, if you don't want to start to make B and C, you don't want to start with a double bond. You just want simple cyclohexanone. It's like simple cyclohexanone. You form a LDA, you form an enolate, and you can react to butyl bromide. And of course, this up here is simply the product of reacting butyl lithium with cyclohexanone. So you can make any of these compounds. Okay, now let's do something a little bit different. Another really good class of nucleophiles for doing conjugate additions are, it turns out, enolates. You make an enolate. The enolate itself can behave as a nucleophile, and it's not that great of a nucleophile, so it will do conjugate addition as opposed to direct addition. So let's do an example of this. So here's a simple aldehyde, and we throw in some base. And if you didn't have this compound over here, if you didn't have the conjugated ketone, this would do an aldol condensation. But it turns out that this guy here is a very good substrate for this, so this will do conjugate addition as opposed to simply doing an aldol condensation. You might get some of the aldol condensation going on as well. It's a competition, but you can indeed do the conjugate addition of this. So what we're going to do is form an enolate here, do a conjugate addition. So can you see what the product is going to be? You should be able to figure this out because it's doing conjugate addition, so you know it's adding down here. So let's go down here. A doesn't make any sense, B doesn't make any sense, C doesn't make any sense, D doesn't make any sense, E, now we got it at the 4 position, that's good. F's got it at the 4 position. But one of them still has the double bond. Which one is it? The one with the double bond or without? Well, of course, it's without, because when we do the conjugate addition, we're going to get rid of the double bond. So we're going to start by forming the enolate. It's going to reach. Oops, I have to do it again. It's going to reach, it's going to form, run over, attack the double bond. We're going to go to this enolate, and then we had some water, and we'll go to E. So that's conjugate addition using an enolate. Works really well. Run through it one more time. We form the first enolate. It attacks, does 1,4 addition, gets a new enolate. We protonate. We go on. So that's very good, clean chemistry. So let's do another one. Okay. So this is I forgot to say, this has another name. People love to name all these things. And conjugate addition with an enolate has a special name. It's called Michael addition. And so if someone says this is a Michael addition, it's 1,4 addition with enolate. Now it turns out that people screw this up, and some people will use Michael addition for any 1,4 addition. So conjugate addition, 1,4 addition, Michael addition are all talking about basically the same reaction. Although in principle you're supposed to use the words Michael addition only for the one with an enolate. But who's counting? All right, so let's do a Michael addition here. So what we're going to do is a conjugate addition with an enolate. So here's the conjugated ketone. So obviously we better make the enolate from this guy over here. So can you predict the product? So how are you going to figure this out? Pause the video. I know you never pause the video, you just keep watching, but pause the video. Let's try to figure this out. And while you're figuring it out, I'll give you some hints. So you're going to form the enolate here. It's going to tack over there. You're going to get rid of the double bond. So you just want to piece this together. I mean, these molecules all look pretty complicated, but which one is actually correct? Can you find it? Okay, you're just waiting for me to tell you the answer. I know that. Okay. All right, let's go. Okay, so we'll form the enolate. We're going to deprotonate. There's our enolate. Now it's going to come up here and attack. Okay, and what are we going to get? We're going to get this guy. We're going to throw in some water, and it goes to B. You knew that because you figured it out on your own. That's very good. Congratulations. And so these are somewhat complicated problems, perhaps. But the main thing is you want to do such things as count your carbons correctly, pay attention to the detail, and you'll be able to figure them out. Okay, so let's do another one. So here again we have a conjugated carbonyl, and we have this methyl cyclohexanone over here. So the question is what the product's going to be. Now, how do you figure this out? Well, the first thing you have to do is figure out which enolate you're going to do. Well, what you want to do is you want to find the most. This is hydroxide. It'll give a mixture of both enolates, but the one that's going to dominate is the more stable one. So which the most stable one will be depends upon which hydrogen is the most acidic, which is another way of saying which anion is more stable, which hydrogen is most acidic is the same as asking the question of which enolate is the most stable. And of course, the enolate stability, the one with the more substituents, it will be the more stable one. So that's the proton we want to pull off. So there's our enolate. Now you want to do the conjugate addition. You do the conjugate addition here, and what product are you going to form? Well, again, stop the video, see if you can figure it out. Okay? So, have you stopped the video? I can wait as long as you can. You don't think I can wait as long as you can. Okay, well, anyway, let's talk about it. So, we know this coming to the side with the methyl. So, these ones are the dangling methyl out here. A, B, E, we can kind of throw out, okay? And so we know we're going to add here, so that C looks good. What else we got over here? We got D, it's adding the wrong side. D doesn't make any sense. So what about F down here? Well, again, it's the same thing. Do we keep the double bond or we throw it away? Well, the double bond's gone. So it's C. So we're going to do a conjugate addition like that. We're going to protonate, and we'll go to C. So we get molecule C. Now, wasn't that exciting? Well, it gets more exciting. This is called the Michael product because it's the product you get after the Michael addition, the 1,4 conjugate addition using an enolate. Now, the thing of it is we're not done. Because look at all these carbonyls up here. This thing's a diketone, and we're still sitting in base. And of course, the diketones themselves, we've already seen, can do a self-condensation. And when they do a self-condensation, they form a ring. We saw that chemistry last week. So let's think about that. We still have base, and we still have acidic hydrogens. So there are 3 acidic hydrogens. Each carbonyl, you look at the alpha position, this one has There's no hydrogens here, so we only have 3, not 4. But which one of these would go? Well, in a case like this, the relative acidity almost doesn't matter, because the final product is going to depend upon the stability of the product more than which hydrogen you start off with, because such things as ring size is going to be really, really important. So let's just go through and do them one at a time and see what we get. So let's start off with taking off the first hydrogen, the left over here, and doing we'll do a condensation. We'll have the enolate attack the other carbonyl. So here we go. Attack the other carbonyl. We can number the carbons, and you'll see you have carbon 1 over here attacking carbon 6 over there, and we're going to form this lovely little species that looks like this. Now this is actually, you're forming a 6-membered ring, but it's kind of this bicyclic system. It looks actually well, it looks pretty ugly. All right, and that's just an ugly molecule. We're not going there. We're not going to go there. So let's try this one. And now we attack there. Okay, and that's, what does that give us? Well, it's going to give us a pretty small ring. What is it? It's 4-membered ring. That ring is, not only is that ugly, it is strained and ugly. Only its mother would like this molecule. I'm sorry, it's ugly molecule. It is strained. We're not going to go there. So let's try our last possibility. Let's try the methyl out here. Let's form the anion there. It can reach around and attack. And again, we see we're making a 6-membered ring. Look at this guy. That is absolutely beautiful. We can, this is still acidic. We got this hydroxyl group as leaving group, so we can do the elimination, form our double bond, and look at that. That is just an absolutely beautiful molecule. So this, it turns out, is a really good reaction. It is called the Robinson annulation because the man who discovered it name was, surprise, Robinson. And he was a very famous organic chemist, and this reaction turns out to be a really important one. For one thing, lots of chemists have used this to make steroids, which of course are a very important part of biological molecules. So let's go through another example and see how this works. Or let's first review this one. It's 2 steps. First, you do a Michael reaction, and then you do an Aldol condensation. And this 2-step reaction ends up, what you do is you're adding a 6-membered ring to the side of another one. And an annulation, that's what the word annulation means. It means adding a ring to basically adding a ring to an existing molecule. So we've added so here down here, if you look at the roots of this, here's the methyl of the original methyl cyclohexanone, and this double bond here is the carbonyl of the original methyl cyclohexanone. So it's kind of buried right here, and what we've added is this 4-carbon unit up here on top. And so that's the annulation. So it's a pretty cool reaction. So, and again, just writing out the whole mechanism, it's 2 steps. You form your original enolate. It does the conjugate addition, the Michael addition. You get the Michael addition product. And now, the way we did it before, you say you protonate and go to this, and then you deprotonate. Well, you don't actually do it this way. And in matter of fact, what happens, you just skip, you don't skip it, you don't do the protonation. I mean, you could do the protonation. If you were very careful, but the problem is this, it also wants to tautomerize and go this way, so this might actually be hard to isolate. So in the real reaction, you don't add in protons. This thing just tautomerizes. You have to do a transfer of the proton from the methyl over here, and then you have a new enolate. It'll cyclize. You lose the water, and you get this beautiful little molecule over here. Okay, so Robinson annulation. Overall, it's a good process. All right. Now, if you look at the formulas of these things, so this C7H12O, 4C4H6O, add them together, and of course, what you're doing, you're missing a mole of water because you should have 18 hydrogens, you only have 16. You should have 2 oxygens, you only have 1. So you've lost a mole of water out of this. So this is a condensation, and the Aldol condensation tells you. The Michael addition, you don't lose any atoms, but Aldol condensation, you do. So we've lost a water molecule. Okay. So let's do another one. And you look at all these things, you can say, well, how do I know what my product is? Well, in this case, I'm giving you the formula. And again, if you add this all up, you'll see that we've lost a mole of water. Because again, 18 hydrogens going to 16, 2 oxygens going to 1. In fact, this is just a very similar case where we're losing a mole of water. So let's go through and do this Robinson annulation. So which of the hydrogens is the most acidic? Which one would you take? Well, obviously it's going to be one next to the carbonyl. It's going to be the most acidic. All right. First of all, I know that's the left-hand molecule because this is the one with the conjugated carbonyl. So this is going to be attacked. The molecule on the right is going to be attacked by the molecule on the left. But which hydrogen? Well, do we take off the hydrogens at the bottom here or the one up there? Well, again, I said before that ultimately ring size is the one that's going to determine which one works. But it turns out both of these would give you a 6-membered ring. So in this case, which one to choose is indeed based upon acidity. And the conjugated one will go there because it's conjugated with the phenyl ring. So if you form the enolate on this side, the enolate will be conjugated with the phenyl, which will be more stable than forming this one up here. So you're going to, the proton you're going to remove is the one that gives you the conjugated enolate, which is D. Okay, so let's go through now. What kind? Well, we know the answer to this. We've been talking about. What are we going? How are we going to do this? We're going to do a simple aldol followed by enolate, or are we going to do conjugate addition? Attacking the enolate attacks the 4 position. In other words, the Michael addition. So we're going to do the Michael addition. There's no mystery. We've been talking about this. So draw the product of the conjugate addition. So you got to form an enolate here. Form an enolate here and have it attack over there. So can you do that? Well, what product would you get? Well, I've got them all dangling off here, and of course, the simple thing is we're simply going to add over here. The double bond is going to disappear. So we get back here. Which one is it right? D is nonsense. C, we attacked the wrong side. Here again, we have double bond, no double bond, and we know by now it's the no double bond. So we get A. Great. So we got A. So here we go. Do the conjugate addition. There's the molecule. We protonate. Oh, for some water. We got A. Okay. Now again, we're all set up to do another addition in the sense of this going to do internal reaction. Now we have to draw the aldol product. So we want to do a condensation of this, and it's simply going to close up nicely to form a 6-membered ring. So see which one it is. Well, I said 6-membered ring. So we got some nonsense with systems up here, but again, which one do you get? Do you get C or do you get B? Well, what's the difference? The methyl group. Well, the methyl group is going to be on the far side of that carbonyl over there. It's going to be B. Okay, so we're going to get B, and you can draw out the mechanism here. You form your enolate. You have attacked the carbonyl. You protonate. Use another molar base to eliminate the water, and you go up there. So this again is a beautiful example of the Robinson annulation, and that should make you extraordinarily happy. Anyway, have fun with the problems today, and that's it for today. So thank you very much.